So my research is in quantum computing. So I'm going to tell you a little bit about quantum computing first. So the idea for quantum computing is to leverage the laws of physics, more specifically the laws of quantum mechanics, for efficient computation and also secure communication. So what's quantum mechanics? I mean, very, very quickly. Quantum mechanics is basically the most accurate theory of physics that we have. It's physics that describes the infinitely small. So the behavior of individual particles, like electrons or photons, or maybe like hundreds or thousands of these particles, but very small. So it's a very good, very solid theory that hasn't changed for something like 70 years. But there's something about it, right? And I'm sure everyone has walked into libraries and seen books about quantum philosophy or quantum healing. Or there's really something about the principles of quantum mechanics that's counterintuitive. And we hear about things like uncertainty principle and no cloning and entanglement and such things. But these are the very phenomena that are exploited in quantum computing. So the field was born in the 80s or 90s based on two outstanding discoveries. The first one by Bennett, Broussard, and a few others is the discovery that using quantum information, you could enable information theoretically secure communication. So you had cryptography that's secure based on the laws of physics. That's the first discovery. And the second discovery a little bit later was that you could, in principle, leverage these laws of quantum physics, quantum mechanics, in order to efficiently implement or solve certain algorithmic tasks for which we didn't have any classical algorithms. The most famous example is Shor's algorithm for factoring. So the problem of factoring is that you're given a very, very large integer, and you want to decompose it as a product of smaller integers. And this is something that we don't know how to do using regular computers, such as my laptop, but was discovered in the 90s that you could potentially do using a quantum computer. So they were like two big bangs, but they were theoretical bangs. Actually, quantum cryptography was implemented like shortly thereafter. So this is a picture of first experimental demonstration of quantum key distribution over something like 30 centimeters. And there's a nice story about this, which I got from a talk by Charlie Bennett, which is that, so what you see in the picture is, I will not describe everything, but on the left there's some kind of a laser. This is a very high intensity, very focused laser that's emitting particles of light, photons, one at a time. And the photons are hitting a screen over there. And you have to imagine that one person is here and trying to send, somewhat simplifying here, trying to send a hidden message to the party here, and the message is encoded into quantum degrees of freedom. But because their equipment was not that good, because this laser required very high amount of power, just by standing in the room, you could hear the sound that the power that goes to the laser makes every time you want to send a signal. And that sound is different based on the kind of signal that you're encoding. So just by listening, you could decode the signal. So this is lessons in like side channel attacks and things like this. At least you could do something, whereas for quantum computing, nothing. So at the time, this was all like in principle, but it's papers. Nothing was implemented. So time passed, and things are changing very fast these days. So in terms of computing, we now see many pictures of quantum computing chips. So I put pictures of the leading companies that I could think of. So IBM, Microsoft, Google, and then some others. These are quantum computing chips that have sizes ranging from 50 to 100 qubits. And it's a little bit of a question what these things can do at the moment, but what I just want to illustrate is that there's a significant improvement compared to the state of the art 30 years ago. We're not yet at the stage where we can implement actual quantum algorithms, but it seems to me that we're getting there. And that's for computing. And for communication and cryptography, we're actually there. So a lot of experiments are made. This is an experiment in the Netherlands. This is an experiment that uses a satellite. So instead, the laser that was my slide before now is a satellite beaming the laser. And you can, this way, distribute secure keys across different points on the planet. All right, so this was kind of my lay of the land, but actually, I don't want to talk about technological progress during the talk. I want to use my privilege of a researcher to kind of like step outside of time and try to take you behind the scenes to fundamental principles and fundamental questions, which is a little bit my motivation for studying quantum computing. It's not only, of course it is, but not only what can you do using quantum computing, what kind of computation, what kind of communication, but also what do you learn about quantum mechanics in this way? These questions about what can I compute, they're questions very unique to computer science, and by studying them, we're getting insights about quantum mechanics. And I kind of want to demonstrate this in the lecture on a very specific example. So I chose it as an illustrative example, but it's a meaningful example. So bear with me. So the example is the simplest, I took the simplest task that you can solve or achieve using quantum mechanics that you cannot achieve classically. Okay, so the simplest kind of quantum advantage, we could say. And it's this, maybe some of you have studied this in physics, it's interferometer. So what's happening there is that you have a laser, the laser is going through some kind of, it's called beam splitter, it's sends the photons in different directions depending on their polarization. You have mirrors that simply reorient the photons, and here you have detectors that are simply screens, and you look at where the photons arrive. This is how it would look like in the lab in terms of the laser and the mirrors. I'm not an experimentalist. I don't actually have a lab, so for me, this is how it looks like. So this is a quantum circuit, and there is something special about it. So this circuit describes a simple initialization procedure where your memory is initialized to a zero state. Then a simple quantum operation is performed on that memory. This represents the beam splitter here. And then you perform a measurement. So the laws of quantum mechanics predict that if you do the experiment, and this is validated by practice, what you will see is that each of the screens will light up with 50% probability. So half the time the photon goes one way, and half the time the photon goes the other way. All right. What's very special about this is that my actual experiment, so the apparatus and the instructions that they gave, is completely determined. This is deterministic. I am always doing exactly the same thing in my lab. Yet, at the outset comes something that appears random, and according to the laws of mechanics is random. So I have a deterministic process that generates randomness. This is something that we do not know how to do using computers. Computers are entirely deterministic devices. If you provide exactly the same input, it will provide exactly the same output. So why is this interesting? Well, randomness in computer science is often seen as a resource, so you can use randomness for many things. It's, of course, essential to cryptography, and here you have to think of randomness as uncertainty, okay? So this randomness is some information that someone doesn't have about the outcome of your measurement, and that can be used to encode secrets. Of course, it's used in probabilistic algorithms and simulations, such as Markov chain, Monte Carlo kind of approaches. And also, this is a real application of quantum randomness, it's important in gaming rooms. If you have a gaming room, it's actually in your interest that the randomness that's used in your roulette or whatever is unbiased. If it's biased, someone is going to notice and take advantage of it. Okay, so quantum mechanics predicts that there are very simple circuits, such as the one, or experiments, so was the one that I described in the previous slide, that generate randomness. And this is something that ought to be useful. And it is useful, and in fact, the Swiss industry noticed quite a long time ago. So this is a quantum random number generator. I wanted to show it to you, but I forgot. So it's in my office. So I bought this some time back, and you can get it for a few hundred francs. And inside there is exactly what I described before, a laser, and there's a mirror, and you can plug this into the USB port of your computer, and it gives you random numbers. All right, so I forgot to bring it, but luckily we're in the age of the internet, so I can take advantage of the fact that quantum computers are available on the internet, and I kind of encourage anyone curious to play around with them. So I took the IBM. So IBM has a lot of quantum devices that you can access for free from their website. So you just create an account for free, you log on, and here on this example, it's a very small device, 5 qubits. But for my randomness, I only need 1 qubit, so even that is overkill. So I took the best one, it's the one in the middle, and I drew my circuit from before, right? So the beam splitter, like the gate there, and then the measurement. And I told IBM, okay, so do this for me, please. And they did it, and they report the results, and it's pretty good. So like a bit more than 50% of the time they got 0, and a bit less than 50% of the time they got 1. So great, this works. Or does it? So here I kind of can let you read this, and I'm making a step that's perhaps not completely obvious. It's a step sideways. But the question is, of course IBM can calculate what this circuit is supposed to return. They know it's supposed to be 50-50. They're not going to tell me they got 50-50 because that would be too good to be true. So they put a bit of error, and this is what they got. So here we have an interesting question, which is illustrated by the cartoon, which is how do we know? Okay, so quantum mechanics has this nice nature that it's random. Okay, so I can use it to generate randomness. That's a useful resource. But how do I know that I actually generated what I wanted? It seems like I can't. And so I want to take a little bit of time to show you how actually using a little bit more quantum mechanics we can. Before continuing with this thread, let me give you a little bit of motivation to illustrate that even though this is like a very specific question, it embodies much more. So here's the question that we're studying, like certifying random bits through an interaction with a quantum computer. What this already implies or has inside it is what we call test of quantumness. So because classical computers cannot generate true randomness, if I have an experiment that allows me to certify that some machine has generated randomness, then in particular that experiment certifies that the machine is not a classical machine. It's something that demonstrates quantum. And this is something that companies building chips and things like that are kind of after, because they want to demonstrate that their equipment, demonstrate that it does something you couldn't do without them. And it turns out, and this is part of my research, but I won't describe it very much, that randomness is kind of a building block to many things. So in one direction, I already mentioned this earlier, you can think of randomness as uncertainty, so introduce privacy considerations, and use protocols for testing randomness, leverage that in order to get protocols for quantum cryptography, in particular quantum key distribution. So that's in the direction of cryptography, and in the direction of computation, you can leverage certifying randomness to certifying certain quantum memories to certifying quantum computations. So building on what I'm going to describe, you can develop protocols for verifying an entire quantum computation that would be delegated to a quantum server. All right, so that would be the roadmap, but actually for the talk, I'm just talking about the middle part, random bits. What makes the question interesting is that when we try to tackle it, we hit upon the very same phenomena that make quantum mechanics interesting or powerful theory for computation. First of all, what makes quantum mechanics useful for algorithm is that it exhibits what's called exponential scaling. So in general, if you try to model classically and simulate the state of a quantum device, you will need an exponential amount of resources, that's exponential in the size of the device. So small devices like the one that I described, this you can do by hand, but as they grow bigger, you can do it using calculators and then supercomputers, and the latest devices, you just cannot simulate it directly. So how can you verify a process that you cannot run any simulation about? So that's one question that's interesting. The other one is that even setting aside this simulation question, you have a fundamental problem that quantum information is intrinsically not observable or not clonable. So whenever you make an observation on the quantum system, and this is like the Schrödinger's cat example, the very fact of observing it disturbs it. So you're trying to characterize this quantum system that's supposed to produce randomness. You're going to make some observations on it, and every single observation that you make will perturb the system. And then what do you do? Okay, so you have to restart. But then you wanted to make all these observations, but they're not compatible with each other. The system gets perturbed, and that's just an obstacle to certification. All right. So now back to the problem of certifying randomness, and to explain a little bit how we approach it, I want to introduce the conceptual framework in which a lot of my research operates, and this is a framework that comes from complexity theory, and it's the theory of interactive proofs. So let me say, or try to say a little bit about what's an interactive proof. So what do we do in complexity theory? So in complexity theory, we classify computational problems according to their difficulty. And this difficulty can be measured in different ways. The most standard ways would be according to the amount of time or memory that's required to solve a problem. But you can also look at slightly more exotic features of a problem. And the one that I'm going to look at is not how hard is it to solve the problem, but how hard is it to verify solutions to the problem. So let's take an example. So imagine that V stands for verifier or verification. So this is you, and you're given as input a certain computational problem that you might want to solve. Example, the tree-coloring problem. So you're given a description of a graph, and the question is this graph tree-colorable or not? So can I assign one of three colors to each of the nodes? such that each edge has nodes of different colors. Okay, so in an example like this, you might be able to eyeball the answer and figure out that, yeah, maybe it's three-colorable, like you color this in red, this in green, etc. But in general, for a very large graph, this will be very hard. However, this problem does have a distinctive feature that allows me to classify in some way, which is that even though it might be hard to figure out an actual solution, it is easy to verify solutions. So if you imagine now that you have access to some more powerful entity, P stands for prover, that entity can in principle provide for you a proof that the graph is three-colorable, because three-colorability is easy to prove. You just give the coloring. Once I'm given a coloring like this, very easily going over all the edges, I will check that all the edges are bicolored, and so fine, this is a proof that my graph was colorable. So we give a name to all such problems. We call them problems, or name to the class of such problems. We call it the class NP, and that's a famous class of computational problems in complexity. Now the story doesn't end here. Some problems don't even have efficiently verifiable proofs. Here's an example. Just flip the problem, not three-colorable. So you're given a graph, this one, and you're trying to decide whether the graph is not three-colorable. So this one, you can probably do it and figure out that because there's 4 nodes and they're all connected, it's not. Okay, you can't do it. But what if the graph was bigger? So in this case, if you think about it, it's not clear what the proof would be. How do you prove to someone that the graph is not colorable, except by telling them, just try, and you'll see it doesn't work. So this problem is a problem that's not known to be in NP. So not only it's not efficiently solvable, or not known to be efficiently solvable, but also it doesn't have efficiently verifiable proofs. What it does have is that it has efficiently verifiable interactive proofs. So I'm inserting a new ingredient here, which is that I don't expect the proof to be a static object like this coloring that I can verify, but instead I allow myself to engage in interaction with the prover. So maybe I will start asking, can you please tell me this about the graph, and what about this, and explain this in a different way, etc. And through interaction, we're able to verify more complex properties than without interaction. This is demonstrated. This is a result that's demonstrated in complexity theory. So IP stands for interactive proofs. Now it's going to be relevant for what will come later, that we can take this one step further and study interactions not with one entity, but with 2 entities. So what's the point? Now you can ask questions to 2 persons, but these questions are infinitely powerful. They can answer each of your questions, so why have access to 2 of them? Well, think that you're trying to verify the information that's provided by them. And it's well known in police circles that if you have 2 entities and you're trying to verify that they're giving you information that's correct, the thing to do is to put them in separate rooms and ask related questions. Okay, so that's what you'll exploit here. And using interactions with 2 provers, you're able to verify exponentially more complex problems than you could with just 1 prover. This is something that I'm just stating, but will not demonstrate. So complexity, then we like to write equations like this. So that's the E equals MC squared version of complexity. That what we do is that we take complexity classes and we relate to each other. And the equation is interesting if it relates classes of problems that have very different definitions. So this equation is interesting because it relates problems that you can verify through interaction with problems that you can verify in exponential time, but bounded polynomial space. Okay, so there's a similar equation that characterizes the multi-prover version. All right, so this was complexity background. It's not too important to understand everything that I said, but just to have in mind that you have this framework that, using interaction in different setups, you gain additional power in verifying certain computational problems. Now, here, arrives quantum computing, and we have many questions that we might ask about our model. How is it affected by quantum computing? Okay, so now we have quantum computers everywhere. So this verification is quantum, this device is quantum. The interaction can involve quantum information. And we can ask what problems can be verified in this way. And we give it a name, QIP, and we study it. Similar here, so we can allow quantum information to everyone. We can also allow quantum information across the 2 devices, something I'll talk in a few minutes, and ask what problems can be verified in this class. So when Rudiger earlier talked about MPI star, he had a bit of a typo. It was meant to be MIP star. Rudiger, please correct your slides. So this is something that I studied in my research. But I don't really want to go there. I'll go there a little bit later. Right now, I want to specialize these ideas to the problem of testing randomness. So we're back here. We have this device that we bought. and we're trying to verify that the device generates randomness. And we have this idea, because of what I said before, that maybe by interacting with the device, kind of like asking different questions, we might be able to get a handle on the kind of information that it's generating. But to get started, we need to ask ourselves, where does this randomness come from? Like, why do quantum mechanical phenomena generate randomness? You can have a couple ideas. One of them is the uncertainty principle. So Heisenberg's uncertainty principle states that there are fundamental properties of elementary particles, for example, position and momentum, that are such that it is impossible, so there's a fundamental limit to how much you can determine one property or the other. So one of them can be fully determined, the other one will have some amount of randomness. So that gives you an idea. Here's the experiment that I should design. So I will prepare a quantum particle, this photon, and I will make one of two measurements on it. So instead of always measuring it in the same way, like I did earlier, I will either measure some property of it, like its position, or its momentum. And I know that by Heisenberg uncertainty, whatever is the state of the particle, one of these two measurements will generate randomness. So it's a good start, but it's not enough, because we managed to say whatever the state of the quantum particle, but we didn't manage to say whatever the measurement that's made. So this uncertainty will only kick in if I make very specific measurements like position and momentum. But who knows what measurement is being made inside the box? Okay, and actually, if you think about it, this is never going to work. If I have an interaction with the device and I ask it, please do this, please do that, report the results, as long as there are some results that I have a chance of accepting, there will be some deterministic result that I will accept. Whatever is the correct answer, they could in principle figure out. So we need to go a little bit further. And to go a little further, I will call Einstein to the rescue, if I may. So Einstein was famously bothered by this randomness in quantum mechanics. He thought, no way, this cannot be the case. It's a problem with the theory. There's something that we don't understand yet. So he thought quantum mechanics is not complete. And in his quest to demonstrate that quantum mechanics was not complete, he came up with a number of thought experiments. One of the most famous ones is the EPR, Einstein-Podolsky-Rosen thought experiment. And this thought experiment, I will describe loosely speaking because it will be useful for us. So the thought experiment is based on the notion of entanglement. So Einstein and others observed that quantum mechanics seemed to allow you to generate states of, state of two now quantum particles that are so-called entangled. And what this meant is that whenever you make a measurement on one of the particles, any measurement you like, position, momentum, whatever, if you make the same measurement on the other particle, you will get exactly the same result. Okay, so if you measure position, you will get the same. If you get momentum, you will get the same. But that gave him an idea. So suppose that I'm interested in the position and the momentum of the green particle on the right. All right? Well, I could measure the position of the one on the left. Now, if I measure the position of the one on the left, I know that if I measure the position of the one on the right, I will get the same outcome. So let's not do it. Let's just have measure the one on the left. Instead, let's measure momentum of the one on the right. And now I have a way to measure both position and momentum of the particle on the right. But that contradicts the uncertainty principle, so there's a bug with quantum mechanics. Okay, well, this was not expressed with exactly in these ways, and it was a little bit obscure. There's no bug with quantum mechanics. What there is that whenever you make a measurement on one particle, learning the outcome of the measurement affects the state of the other particle. And so when you measured the momentum on the first particle, later you measure the position of the second particle, actually the momentum that you measured will not be the momentum of the other particle. This is not so important. What's important is that you have this notion of entanglement that is such that by making identical measurements on the two particles, you always get the same outcome. Actually, you can go further, and this is work that's after Einstein, like work in the 60s. Correlations characterize entanglement. So you can list all possible correlations between different measurements that you could make on an entangled state and list the probabilities that you would get. And it turns out that these probabilities characterize the quantum state that's being measured. Not only the quantum state, but the measurements themselves. So in other words, if you imagine an experiment where different measurements are being made on these two particles, and you list all the statistics that you get, so you repeat the experiment many times, and you just list averages, there are certain statistics that will end up characterizing the quantum state of the device. Now, this gives us a solution to our problem of testing randomness. So instead of imagining that I have a single system, I'm going to imagine that I have two systems, and these two systems are initialized in a quantum entangled state, so in a specific state called an EPR pair. And then I will interact with both systems, asking different kinds of questions. So the questions are, can you please tell me the position? Can you please tell me the momentum? Whenever I ask a question to a system, the system performs whatever measurement it wants, and then it returns to me an outcome, A, which is some classical information that I receive. I can similarly send the question or ask for a measurement on the second system and get an outcome. And it turns out that by checking certain statistics of the interaction, you can verify that the quantum system that was measured is an EPR pair that was measured in a very specific way, and thus obtain a verification that in the outcomes that you obtain, A and B is some amount of randomness. This is kind of like randomness certified by the laws of physics, even for the biggest quantum skeptics. And what we had to do, my point was that in order to do that, we had to kind of like step a little bit outside of the box, in a way, change the framework and introduce an additional quantum phenomenon, entanglement, in order to certify the randomness. So, what's my time? Okay, I have a couple more minutes. Finished? Huh?
You have 8 minutes left.
So I should stop soon. All right, so I will say just one more thing, which is like now I'm like zooming very fast in the future and telling you consequences of what I just described for complexity theory. So in complexity theory, it's known that, and I mentioned it briefly earlier, that in this model where you're allowed to interact with two proving devices, you're able to verify in a relatively small amount of time. So n is a parameter, the size of the problem, n cubed is the time that it takes to verify it, and 2 to the n is the time that would have taken to solve the problem. So what I and collaborators showed is that you can leverage this in order to do more and more and more. So the idea here is to say, well, I have this procedure V that's supposed to perform a verification. Verification is a computation. So why don't I offload this very procedure, the verification, to the servers themselves? And you can do that, and what enables you to do that is that through the entanglement, you have a very fine control on what the quantum system that's held by the provers can do. So you can tell it to kind of like verify yourself. And in this way, you're able to, in the exact same amount of time, n cubed, verify problems that need exponentially more time to be solved. Okay, and then you can continue, and you can repeat this many times, iterate it, and get surprising consequences. So maybe I will end here. One is the one that was mentioned by Rudiger. So you can design efficient verification protocols that verify arbitrarily complex problems. So this equation is an equation in complexity theory, but it's interesting because on the left-hand side, you have a class of problems that is defined through quantum mechanics and interaction and verification. And on the right-hand side, you have all problems that can be all problems such that there's an algorithm that will eventually return the answer of the problem when the answer is positive. I didn't say that very well, but it's a very big class of problems that in particular contains undecidable problems, such as the halting problem. And thanks to the fact that the laws of quantum mechanics are very pretty, and they were born through the work of von Neumann in the 30s, which went on to develop von Neumann algebras, a lot of the work in quantum mechanics tends to have repercussions in mathematics, and this is just to try to impress you by showing you an equation that probably no one in the audience can parse. But this is just some work about relating different norms on tensor products of C-star algebras. But it also has applications for theory of graph limits. So to conclude, I'll just mention one direction in which I'm interested in taking some of the work that I talked about. So I talked mostly about bipartite correlations. So these are strong quantum correlations between two quantum states. Entanglement can take very different forms, and a particular form is one that exists in many-body systems. So these are the systems that are useful to design. They arise in quantum chemistry, for example, when you study quantum molecules, or in the design of superconductors. And an entanglement in that regime, when it's kind of like diffused between many particles, is very poorly understood. We don't have very good tools there, and it's something that I'm interested in. So let me end by thanking all my longtime collaborators. So many more people contributed to the research that I mentioned. These are the ones that have been with me for a long time. So I thank all of them for their great company and great ideas. And I'll stop here.